Yeah, they both work.
Okay.
Okay, cool. We'll get started. Thanks for coming here. So Yelp has been a big Mesos user for maybe 3 years now, coming up 3 years, and we still continue to build new and interesting systems on top of it. So today we're going to share with you a system we've been working on for a few quarters now called Jolt. I'll let Timmy take over.
Right. Thanks, Sunil. Okay. So, yeah, I would like to talk to you about Jolt, a system that we've been working on for past few quarters. And we're kind of need to run tests in a distributed way, and Jolt is something that we've been working on to kind of let us do that. So, who are we? So, I'm Timmy. This here's Kyle and Sunil. Uh, we work on teams at Yelp that help to maximize engineering productivity. Um, we want to help all the developers at Yelp uh, make changes to the Yelp site and services to let them make those changes as fast as they can while keeping the site reliable and available to users. And we also work on providing review, building, and testing infrastructure for developers at Yelp. So Yelp's mission is to connect people with great local businesses, and the work that we do to improve the system so that developers can make changes directly influences that mission. So when Yelp operates at the scale to execute on that mission, to reach tens to hundreds of millions of users across mobile and web every month, then the more improvements we make to those systems to let developers iterate faster and with more confidence, and the faster they can improve that experience for our users. So how does that tie back into this making tests run faster or more distributed? Well, Yelp runs a lot of tests. We have a legacy monolith application, which has over 85,000 tests. And we have a lot of other services too, which all have their own tests, hundreds, thousands of tests. So all in all, there's over 100,000 tests across all the code that we have. And whenever we deploy a new version of that code to production, we want to be sure that it has a high probability of not breaking the site. So before deploying code, we would like that everyone run all the tests for all the tests in the service before they deploy. So it'll be prohibitive for everyone to have to run all the tests on their own. Those 85,000 tests aren't just going to run themselves, over the course of the day. Maybe it could be a week before they finish. That's a lot of tests just to run serially. So one thing that we want to do is parallelize the test runs so that they're a lot shorter and developers can quickly get feedback on whether the change that they've made has broken the site in any unexpected way. And the faster we can do this, the faster we can push changes to the site and make sure that we're not actually breaking the site by pushing it so often. So this is not a subject that's actually totally new to us. We already have a system that we've talked about before publicly that aims to solve this problem, and that system has existed for almost 2 years now, and it's called Seagull. So Seagull is already operating at scale in our engineering organization. Seagull runs 350 test runs a day. So when a developer needs to test their changes or their version of their code, then they kick it off, and that happens 350 times a day. There's people that run one time a day, or maybe they are not really sure of the changes and they run 10 times a day. But all in all, there's 350 of these kicked off, and we managed to make it take only 10 to 15 minutes. In the course of running these 350 test runs, we spin up and then tear down 2.5 million containers. Some services need to spin up data stores. Some services need to spin up other service dependencies. So whatever those containers are, we have to spin up and tear them down a lot. And that sometimes takes a lot more time compared to other dependencies that a test may need. And Another thing that we do is the cluster that these tests run on. We scale it from 70 instances to 450 instances because developers, well, we only really need the cluster to be running tests when developers are submitting things. There's no point to having so many machines in the middle of the night. But when people want their tests to be their changes to be tested, they're not going to want to wait either. So we have an element of auto scaling the cluster so that it's right sized with respect to how people are developing and making changes and expecting feedback on those changes. So across all of those things, 350 test runs, cluster that scales up all the way to 450 nodes, then and back down. Then we execute 25 million tests a day, and the feedback from where those tests succeed or fail informs whether those developers can how fast the developers can iterate and make changes to improve Yelp. So given that we already had some prior experience, then why are we, what is wrong with this thing called Seagull? Well, it's not really anything wrong. It's working production today, but we're taking a new look at what we tried the first time around. When we first developed Seagull, it was kind of our first time using some of these systems in production. At the time, we were not really too experienced with using Mesos, not too really experienced with uh, clusters running these tests at this kind of scale and having nodes that could go up, that could scale up or scale down, or a lot of different things that we didn't really quite understand. So in the course of developing Seagull, then we we realized that we actually wrote some components that were not we didn't actually need to write. For example, Seagull has its own executor, even though the way it's structured, there's not really such a huge need for custom executor behavior. We could just use a kind of more generic executor interface that just runs stuff on the Mesos agent. Or we also implemented our own artifact management, which takes care of uploading artifacts to S3 from where the job is submitted, or downloading it to the executor when it's time to run a test, caching it, and all that good stuff. That's not actually necessary either, it turns out, because Mesos has its own functionality for doing that. So there's actually a lot of moving pieces that, when we look at it as a whole, it just adds to the complexity of the system. And when we're writing Seagull, we had it in mind to write it to be able to run our monolith. I mentioned earlier has 85,000 tests. So a lot of that was designed in mind with how that already runs. So it turns out after all is said and done that when we're like, oh, check out this great system we made, you should use it to run your tests too for other services that people are already building on at Yelp, then it wasn't so easy to integrate those services with Seagull. So then we're like, maybe we should write a system that is more easy to integrate so that it becomes useful to systems other than the monolith which we're already trying to chip away at. So in trying to distill what we really want from something that runs our tests at scale, then we kind of chipped away all those unnecessary pieces and built something that which has a skeleton that basically can be pared down into something like this diagram here. You can see that the 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 thing that we're talking about, Jolt, is at the top where a user would submit something to it, and then we kind of split the relevant code into two parts, Jolt and task processing, which is another library that we're also working on here at Yelp, but we're kind of separating the concerns between something that knows how to run tests and something that knows how to talk to Mesos so that we don't kind of end up with such a unitary blob as Seagull is. And Jolt uses task processing as a library to talk to Mesos, the Mesos master, which in turn does its thing with Mesos agents. And once the Mesos agent gets a hold of something to execute from Jolt, then we put all the relevant artifacts, lists of things to run, a way of running them to S3, and then that's how we move around all those artifacts. One of the things that we want to do in Jolt is to kind of split the tests that we want to run into bundles of a certain duration. Especially because if we just wanted to run each test by itself, we could incur a lot of setup and teardown time, spinning up Docker containers, having to pull and whatnot, especially if they're not in the Docker daemons cache already, for example. And so you want to kind of only have to incur that cost once. So we, and among other things, so we split the test into bundles of a certain duration. It's like, oh, this bundle with all the tests in it, it'll take around 10 minutes. So we know how long these tasks are take on their own, and then we kind of bundle them into a set of tasks which we know takes some amount of time. And we also try to make it so that all the tasks in that bundle need the same thing. So it's not like half of the tests in a bundle suddenly need MySQL and then we have to turn on MySQL halfway. And so once we've made these bundles, we submit them to Mesos, and then the Mesos master will distribute them in the way that it does, and then they'll run on each Mesos agent to run the tests in that bundle. And we also want to retry on failures. If a test fails, it's not, we still want to run the rest of the tests that we're looking to run. If the entire bundle fails because there's a problem bringing up the data store or bringing up another service, we don't want that to just cause everything to call quits either. So kind of center around this concept of bundles and figuring out the semantics around retrying and running the tests inside them. So when we bundle, the user that starts a run for Jolt, they specify how long each bundle should take. And then we bin pack the tests into bundles using the duration that we know each test will take. So we're storing the duration of the tests from prior test runs. When it comes time to bundle, we grab all the timings for all the tests from Elasticsearch and then use that as an estimate for how long it'll take. Hopefully it's close enough when we're just using a simple rolling average over time. And when that run finishes, then we update the average in Elasticsearch. So simple enough, it's just using the times that we've seen in the past and using that to make an educated guess about how long it'll take when run by itself, using those to create kind of equally sized bundles of tests to run. So how exactly do you interact with this system in real life? You can't just interact with like a diagram of little colored blocks, right? So try to keep it fairly simple. It looks like there's a lot of options here, but they're just kind of options to control how we interact with the bundles. The things that are really relevant here, you can see is a testrunner.sh, test.list. So those are how to run the test, given some amount of tests that will slice and dice by bundling, right? And the tests, of course, we need the list of all the tests. And hopefully the project has some other files such as like the tests themselves or actual code to run. And you can specify an arbitrary number of those by the artifact argument there. And there's a few other pieces of metadata, like I was saying. We know what this project is, or how many times do we try the bundle, or how big to make the bundles, or how where to put the results of the entire run after we're done, or even environment variables that maybe when the test runs is influenced by some environment variables that are set under test, for example. So we know how to set those as well because it's a common occurrence that people have this kind of arrangement in their testing. So we try to keep it fairly simple. Again, the really relevant things, the actual code to run, there's like a tarball, how to run it, and what to run. And to support this code, it's just like, so far that command line interface has just been talking directly to Mesos master, but we have some supporting infrastructure around it. I mentioned earlier that we use Elasticsearch to store and retrieve and update the durations of the tests that we saw. And since there's like I mentioned, we have 85,000 tests in the monolith that we have. It's actually not that small amount of data. You having to fetch all the estimates for the every time you want to uh, do bundling means that actually you're fetching like most of the data that's stored. So it's not actually not that small amount of data. And considering that again, developers submitted 350 runs, is actually fairly high amount of traffic just to get these test estimates and update them as things finish. And we also report the result of the test run to another application that we have for our developers called test results. It the the code that's being tested will report via Kafka about how what the result of the test was, like the exceptions and what how many failed and what those failures were. Those are emitted to Kafka and then collected in Elasticsearch, and then developers can see what actually went wrong, how many like all the tests that have the same kind of exception, or whether those exceptions happened uh, in the past, just to kind of determine whether what the changes that they made, is it due to the changes, or has that been broken all along? And the other thing is that we still want to auto scale these clusters, because again, the amount of runs that are being placed really is all driven by developers' workflow, and the developers are not going to be really working, hopefully, in the middle of the night. So I want to keep that auto scaling behavior. With that, I'll turn it over to Sunil, who will explain more about these other pieces.
Hi. Okay, so I'm going to talk to you a bit about task processing, which is the sort of yellowish thing there, and then we'll add some more boxes to this diagram. So what we mentioned was that Seagull was this sort of monolithic framework where it was just one thing. What we did was, as we decided to rewrite it, sorry.
Would you speak up a little bit louder?
Sure.
Thank you.
Okay. So I mentioned that Seagull was a monolithic framework. When we decided to rewrite this, we wanted to actually abstract out the functionality that talks to Mesos and put it into a separate library. So we actually open sourced this a few months ago. It's getting to the stage now where you're welcome to go and use it in your applications. We have this thing called task processing. It's on our GitHub. So task processing uses the new HTTP scheduler APIs using PyMesos, and it's intended to be composable. So that lets us use it for lots of different applications. Right now we use it for both Jolt and a replacement for Chronos that we've built here called Tron. So task processing provides a very generic interface that lets you do 4 things, 3 of which are very straightforward. You can run a task, you can kill it, or you can stop it, where stopping is more graceful than killing the task. And you can also inspect the queue of events going to it. This is good because it means that we can sort of draw a line here and say that anyone who's using this library shouldn't really need to know that they are using Mesos. And so, all they really want to do is run a task in a distributed way on a cluster of machines. So I mentioned the implementations are composable. There are a few different types. So we have this idea of an executor, which I introduced earlier, and then we have 3 implementations right now that we provide, but you can override these and write your own, or use any combination of these. So the most basic Mesos executor just lets you schedule tasks on Mesos. If it fails, it fails. It doesn't try to retry, which brings us to the second one, which lets you retry a certain number of times. And then finally, you have a timeout executor that starts the task. If it doesn't finish within a certain time, kills it and reports a failure status back to the user. I mentioned some more boxes being added to this diagram. So we've got 2 more things here. We have this green box, which is ClusterMan. It stands for Cluster Manager. And then we have this idea of spot fleet requests. So as Timmy mentioned, developers at Yelp don't work all the time. And so this is sort of shown in this idea of our average load. So you'll see that during the week, it sort of peaks in the middle of the day, and then on the weekends it drops to 0. We have dev teams here and in Europe, and so there is a sort of constant baseline even when the US is asleep, because people in Europe are using clusters. The same goes for the sort of day-to-day workload. I mentioned that people in Europe are using resources sometimes. So in the morning, early morning San Francisco time, we'll see that our European colleagues will actually push code, and then later in the day, the US employees come in. There's a code push in the morning, so people are running tests. People go to lunch, kick off their test runs as they go and get some food. And again, in the afternoon when we do a push then. So as part of Jolt, we're building this thing called Clusterman, which is an autoscaler. And the autoscaler basically takes a pool of Mesos agents and scales it up and down depending on what the work or the workload is like. And Clusterman also has this idea of simulating how autoscaling behavior will change if we change how much we pay for instances. So I mentioned this idea of, or this concept of a spot fleet. This is an Amazon concept where you're able to actually bid on unused instances that they have available and other people have reserved but are not using. So the way this works is, given a set of unused instances, users who wish to run things on those can bid a certain amount of money. This is usually less expensive than reserving the instance yourself, and Amazon is really just trying to keep the spare capacity in use. So what happens here is a set of users will place bids, and then the people who have the highest bids will get the instances, but they will all pay the price of the lowest bidder who gets an instance. So in this case, users A, B, and C have bid $2 or greater, and all of their requests are fulfilled, so they all pay $2 for those instances. In this example, user B, who has bid $3, wants more instances. He bids more than user C. User C loses their instance, and user B gets the remaining instances. So we use this as part of another feature called Spot Fleet Requests that allow us to take a set of these instances and request all of them together. So this means that instead of requesting one type of instance, we can request 2 or 3 different types of instances in multiple availability zones. And this is nice because demand for instances is variable. And we might find that one type of the day, someone comes online, wants to run a big batch job, something like that, and the price for a certain type of instance goes way up, and we're outbid. Availability zone, too, makes a big difference because people, when they bid for instances, usually want things in the same availability zone. The sort of canonical example of this is someone who wants to run a big MapReduce job or something that requires a lot of batch processing power. So having a simulator actually helps us understand how we can change our bid prices to reduce instance churn or take it to a level which is acceptable and still not spend that much money on instances. So autoscaling is actually also based on multiple things. The sort of easiest thing to do is to look at CPU utilization. In our case, we actually look at allocations. So if you have a certain amount of tasks deployed to your Mesos cluster and it's greater than 65% for 15 minutes, scale up. And then we have some slightly slower scale down behavior. So if allocation is less than 35% for 30 minutes, then you reduce instances. You can also look at other things, like the number of test runs in flight. And you can do some more interesting advanced things too, like looking at the predicted load, which is something one of our interns was looking at this summer. The caveat using Spot Fleet is that given that we have this request for a number of instances, we can't say which ones we want to remove. So our autoscale has to actually go and do this for us, where it goes and looks to see which instances are idle and then terminates them directly. Then it readjusts the capacity, and then Spot Fleet brings us down to what we need. So this is really powerful because it's helped us reduce the cost of running these tests at scale significantly. So this graph is taken from Seagull, which has been running in production for a while now. And you'll see that after we introduced Spot instances, we saw a 55% reduction in costs. And then we added autoscaling in December 2015. And we took this cost savings even higher and saved an additional 60%.
Hey, I'm Kyle. I'm going to talk about some of the challenges and other things that we've experienced while doing this work. So the first one is something that task processing ran into. The new Mesos HTTP API is considerably not as performant as the old protobuf one is. For example, when we started using the HTTP API timeouts in API in production, we saw a significant amount of timeouts. This Mesos cluster and Mesos master had already been running a marathon instant framework with hundreds of applications and then just less than 10 HTTP API schedulers when we started seeing that. Another big problem, specifically with running tests, is Yelp main monolith, and most test suites in Yelp are not fully containerized. They actually expect to be able to spin up their own containers, and the tests run just as a bare process on the computer. This means that these tasks can kind of do whatever they want. That means spin up a bunch of containers, leave them around, fill up the disk, peg CPUs. So we have to do a lot of reactive and proactive things to guard ourselves from bad tasks. One cool thing that we're doing is Docker Reaper. Docker Reaper is basically run in front of the task, creates a new Unix socket for connecting to Docker, and we have a monitoring process that monitors calls to the Docker API, and then once the parent process dies, we'll actually go and make sure that any remaining containers are killed and cleaned up, thus saving us from this world where all of the hosts slowly build up orphaned Docker containers. Yeah, and so some future challenges that we're trying to tackle right now. One of the biggest ones for Yelp main is actually mitigating setup and teardown time. We're willing to vastly parallelize the tests and pay for the host to do so, but the actual just fixed startup and teardown cost of building the environment to run the Yelp main tests in and then tear it down is pretty high. It's like within a minute or two. So actually not having to do that would be great. So we want to send subsequent bundles with the same requirements to executors that already have set up these resources so that they don't have to do that themselves. Another big thing is bidirectional communication between framework and executor. Really what that means is executors have lots of cool information, useful information for the framework that we want to get back. Things like requeuing bundles from bundles, being able to allow executors to report their per test timings themselves so they can be more accurate, so that we can get better estimates in the future, and things like actually reporting whether or not what the actual outcome of the bundle was directly. And then the big one that we've kind of solved in the past with Seagull, but would like to kind of iterate on more, is cluster-wide resources. This is things like shared database instances that multiple executors all connect to collectively, or any other kind of fixed resource. Like, for instance, our Selenium grid provider only allows certain number of concurrent connections to them, and that's true across all of our tests running in concurrency. So there's like a hard cap on how many connections we're allowed to actually make. So we actually need to kind of track that at a global scale instead of just per executor set of resources. Yeah, and to kind of cap it off, we have a demo of Jolt running. So just for the sake of not having thousands of bundles running, I've chosen to run Jolt's tests in Jolt. Just to kind of give a nice example. On the left, you'll see me running Jolt. And on the right, you'll actually see the Mesos Masters UI. First, you can kind of see just the output and all the options we kind of provide. Timmy kind of went over the big ones, but you can set things like what Mesos to attach to, how many times to retry the bundle, where the results go. Oh, okay, cool. And so now I'm actually going to run Jolt's tests. We have a remote test runner script. I've already generated test.json, which is just all the tests that Jolt has. And then the build.targz is just Jolt's virtual environment plus Python code, pretty much. And Jolt expects CI true, so that it does some smart connecting to some fake services and that it spins up itself. So you can see on the right, Jolt's registered itself with the Mesos master as a framework. On the left, you can see bundles are starting. We can actually see exactly when bundles start and when they finish, because task processing has a neat executor pattern. They have a couple different executor patterns, but we're using their async executor pattern that basically allows us to register callbacks when different events to the executors happen. It looks like bundle 0 just finished. So waiting for the Mesos master UI to update to actually show us that. But yeah, it looks like all of our tests have started. Cool. So when we actually go into the sandbox for the executor, you can kind of see all the code. But there are some special files. This is the tasks file. It basically shows all the different tests that we have. This is probably the unit tests because they all got bundled because they're very fast. So they're under that default 60-second time. And then standard out is just the test pass. You can see the coverage call. It all just ran in talks with PyTest. Cool, and it looks like we have another bundle finishing. So actually, the rest of our bundles are all single integration tests. So all the integration tests are being run in parallel. Just waiting on the master to actually recognize that it's done. Yeah, so for instance, we're actually leveraging the requirements that Timmy talked about earlier. So integration tests run with the integration requirement. That means that we just make sure to spin up a bunch of Docker containers, things like fake S3, fake Kafka. But yeah, there's just one integration test in the test list, and then more PyTest output that we actually ran the test. Cool. And so, yeah, that's pretty much it for kind of what to expect. Output's still a little developy. Mesos still likes to give us all of its logs so that we can kind of see what's still going on there. But yeah, so all the tasks are still kind of finishing up. And then I've opened up the results.out file. Basically, we just have a JSON blob output where every bundle is kind of attached to a success variant Boolean. You can kind of introspect on what tasks each bundle had, how long they took, what the task name was, what resources we gave to the task. Yeah, and then so, for instance, some of these unit tests you can see have a CPU of 0.1 because they're unit, they don't need really anything. And then later, you can, as I scroll down, you can kind of see integration tests had CPU set higher because they actually need to run a bunch of Docker stuff and are kind of a lot more CPU intensive. Yeah, that's pretty much it. Cool. So yeah, that's it. Yelp is hiring. Our main engineering office is the one you're in right now. This is where most of us are. There's also an engineering office in Hamburg, Germany, and a small operations office in London. We're doing a lot of really cool stuff with Mesos, Marathon, Docker, Zookeeper, the list goes on and on. If any of this sounds interesting to you and you're excited about this kind of stuff, you can apply at yelp.com/careers, and that's it. Any questions, comments? Anything? Or you can just come talk to us afterwards. Yeah, cool. Thank you again.